what I'm going to do, I'm going to give you a general picture about this class, this statics, and then I'll come back to go through each chapter, okay? And if you have any questions, feel free to let me know anytime. So let me grab my pen. Okay, so I'm going to just draw a kind of diagram. So the key part in this class, of course, is called the statics. Can you see here? Okay, so the key part of this class static is chapter 4, in fact, because all the fundamental principles are from chapter 4. And then the question is, what is chapter 4 talking about, right? Chapter 4 talk about the equilibrium conditions, or equilibrium equations, or equilibrium state for a rigid body. So basically, we're talking about equilibrium of two-dimensional or three-dimensional rigid bodies. And then, of course, you need to know, if we're talking about two-dimensional rigid body, we should have three independent equations, okay, to solve for three unknowns. So that is basically the fundamental thing, actually, for the whole class. Okay, so for any two-dimensional rigid body problems, if you plot the free body diagram, you should end up with the three equations. Okay? And then if we're talking about three-dimensional rigid body problems, then actually you should have 6 equations for three-dimensional. Okay? We talk about both. The other question you may ask is, when I gave you those equations, when I gave you those questions for you to answer, I'm expecting you for any test, or we already have, we have done with the 2 midterm, now we're just kind of having the finals, right? When I gave you an equation, when I give you a question, I'm asking you to solve for something. But it doesn't mean I just want you to write down that something directly. I'm asking you to show the work, the procedures, to finally end up with your solution. And of course, hopefully you highlight your box, those solutions. But I don't want to see that box only. If I see that only box giving the numbers saying force equal to something in a certain direction, period, basically, I don't trust much about what you're trying to solve, because you don't show me how you solve the problem. And I really want to see the procedures you are trying to solve the problem. Many students may not like to plot or draw the free body diagram. That's really not good. Let me tell you, if you can use a very simple way or ignore something, but no matter what, you show the work, if I try my best, the grader tries their best to understand, you finally get the correct answers, most likely you won't lose credit. But if you are not drawing, or if you are not drawing at all, if you draw a lousy free body diagram, and then your answers are not correct, we have to heavily penalize you. Because number one, you didn't get a correct answer. Number two, we assume you don't know how to draw the free body diagram. Okay? So if you can draw a free body diagram in a very nice way, neat way, and we solve, which is good, and your final answer for whatever reason is not correct, then we assume, or we can reasonably follow your procedures, and we find out the reason you get a wrong answer is because numerical mistake. Because sometimes you might have a chance to make mistakes by punching the different number. If that's the case, you receive very less penalty, because we understand physically you are doing nothing wrong, but for whatever reason you didn't punch your calculator correctly. But if you do not tell us the story you're trying to solve the problem, and you did not draw the free body diagram correctly, then there's no consistency. Okay, so for example, you didn't draw forces, and then when you write those 3 equations, I saw all those forces, then how can I assume you understand the problem? Because what you're writing is not consistent with what you're plotting. Then you may say, well, I don't want to plot anything. If that's the case, if you can write down those equations very nicely, all correct, that's probably no problem. But if you are not writing those equations correctly and you could not get a correct answer, then we have to assume you don't understand how to solve the problem by first going into the free body diagram drawing. The bottom line is I want to see the details about the procedures for solving the problem. Of course, I would like to see your final answer. But if you only want to write the final answer without giving us the details, we cannot assume the way you are trying to solve is correct. So that's why I keep telling you it's important to show the work. I'm not asking you any concept questions. I'm always giving you those real kind of problem-solving questions. And I would like to see the procedure you're trying to solve. Okay? So for whatever reason, if you believe you did something wrong, you need to cross out those. Some students gave me multiple answers. Okay, so on this left side for this problem, they solve it. And for whatever reason, they thought, well, this may not be correct. And then continue to start on the right side to resolve the problem. And give me 2 answers. How can I decide which one is right? You need to decide. If you believe the right side is correct, then cross out the left side. If you believe the left side is correct, then cross out the right side. If you ask us to decide, we're going to decide the bad one for you. Okay? So do not assume we're going to collect the correct answer for you. It's not our responsibility. If that's the case, we can solve everything for you. We don't need you to take the test. Okay? Because we are testing you, in fact. Okay? So try to understand there's really nothing wrong, but if you believe there's something not correct, you need to cross off that or erase those. Don't leave any confusions. If you let us decide, most likely we're not going to decide on your side. Okay? So back to this one, chapter 4, which is the most important part, talking about the free body diagrams and establishing those 3 equations for 2-dimensional rigid body problems or 6 equations for 3-dimensional rigid body problems. So that's the key in this class. Then there's a special case related with this one. That's in chapter 2. So I'm going to plot chapter 2 a little bit smaller because that's the special case, which is talk about the equilibrium conditions for a single particle. So if we talk about the equilibrium condition for a single particle, that is one material point, then you will have 2 equations for 2-dimensional problems or 3 equations for 3-dimensional problems. Okay, so that's the special case of this. And all the other chapters are pretty much serving for this purpose. Okay, so for example, this is chapter 2, we did it. What is chapter 3? Chapter 3 is a preparation for this chapter 4, which is called the moment and force couple systems. So this part, chapter 3, does not talk about equilibrium condition at all. Okay, so this part basically talk about the moment and the force couple system, which is the preparation for chapter 4. Because those governing equations we obtain are based on chapter 3. Because one of the equations for 2-dimensional problem in chapter 4 is to establish a moment equation. So without chapter 3, there's no way you can establish the moment equation. So that's why that chapter 3 is the preparation for chapter 4. But once we are done with chapter 2, chapter 3, chapter 4, I forgot this is chapter 3, right? Then we are going to have some kind of applications. Okay, just use the fundamental principles to solve specific problems. The first specific problem is chapter 6, talk about truss problems. Okay, so truss problems, we are basically, as a first step, we need to calculate reactions. So that's exactly chapter 4. But after we got all the reactions for the given 2-dimensional truss structure, then our next job is to calculate the internal forces. Okay, so which I'm going to go over those a little bit later on. So this is the one special case. And we do talk about another special case, which is called beam problems, which is chapter 7. We talk about shear and moment diagrams. Okay, and this is also very important. In chapter 6, when we talk about internal forces in trusses, those forces are constant. But of course, you do need to identify it is in tension or it's in compression. But in general, that's a constant. But when we later move to chapter 7, the shear force, which is internal force, and the bending moment, which is another internal force, are no longer constant. And then you have to plot a diagram. And that's called the shear diagram and the moment diagram. Again, do not, I'm going to only get, of course, there's at least one question for the chapter 7, no doubt about it, right? I'm going to only ask you plot or determine the shear and moment diagrams. This is, of course, a question, but do not just plot directly. Okay, so if you do not show the procedure, just plot the final answer directly, there's no way we can correctly evaluate what you did in terms of the procedures. So you do need to show the details. Okay, and then we talk about another two cases, which is a chapter 5 first, which is called the centroid. The reason we talk about centroid is because this centroid is the same concept which we call the center of gravity. So center of gravity is the physical concept. In order for us to make an equivalent assumption, when you have a distributed load, which is equivalent to a concentrated load acting on somewhere, that somewhere is called a centroid. And basically we use the same concept we learned from chapter 3 by talking about the single force system. Okay? And now we finally talk about chapter 9, which is called the moment of inertia. And this is another special case. Instead of talking about the centroid, this time we talk about how rigid the beam is by evaluating that kind of specific parameter we call I. And physically, that I is called the moment of inertia. Okay? So this is basically the whole thing we have introduced in this class. Of course, you may say, how about cables? I did spend just a little bit of time talking about cables, which is part of chapter 7. And I did spend a little bit of time talk about what's called the friction, specifically called the belt friction. That is part of chapter 8. But these two parts will not be covered in the final exam because I even did not give you any homework, right? So you don't need to worry about this. But I did briefly talk about, I just gave you some kind of introduction about those specific structures. One is called the cable, and if they have a belt friction, how you are going to calculate those friction forces. But these two parts will not be covered in the final exam. Okay, and I didn't give you any homework questions either. So this is the general picture. Now what I'm going to do is to switch back to the my lecture notes to talk about what we have learned chapter by chapter. Any questions so far? Okay, chapter 1 is kind of a concept. There's no question from chapter 1, of course, okay? But there's one thing I do want you to pay attention, which is my last slide. That is called the numerical accuracy we need to follow typically. That is what we call the last part, numerical accuracy. But since I just used this my slide, I'm going to tell you now, most likely you are going to take dynamics with either CE80 or MAE80, right, next quarter, because we offer that one. And then most likely when you are entering junior year, you're going to take this class, which is called CE150 or MAE150, I believe. A certain amount of students most likely will take the mechanics of fluid as well. In civil engineering, that is 170, I believe, but in mechanical, I forgot the number. It's probably 151 or something else. Okay, I just want to mention one thing in the last slides, two things in the last slides. This is one thing I want to mention, okay? So when you have a final answer, if the first digit is any number rather than 1, you need to keep 3 digits, okay? So that's the typical. It doesn't mean we have to penalize you if just in case you write a lot of digits, but you should train yourself to have a good habit when you write those numbers. Okay, so this is the kind of widely accepted in engineering community. If the first digit is 1, then you need to finally keep with a 4 digit for your solution, okay? The other thing I want to mention is this. For some questions, we'll be using international system units, right? If that's the case, whenever we talk about self-weight, okay, typically we gave you the self-weight in terms of gram, the kilogram. So you need to multiply with 9.81 to transfer kilogram into Newton, because kilogram is not the unit for force. Okay, it's a unit for mass. If you want to treat the self-weight as a force, then you need to multiply with 9.81. But for U.S. system, you don't need to, because the U.S. system, the self-weight is in terms of pound, and pound itself is the unit for the force. So that's why you don't need to. That's only for international unit. Okay, so there will be no questions from chapter 1 directly, but these are the concepts you'll probably need to implement into any questions you are asked to solve. Okay? Any questions? Chapter 1? So sometimes if you are sitting on the rear side, just talk directly, because I really cannot see whether you raise your hands or not. Okay, so chapter 2, which is a special case of chapter 4, as we can see right now, is talking about statics of particles, or say equilibrium condition of a given particle. Particle means, in this chapter, means it's a single point with no geometry, with no size. So that's why we call the special case of the rigid body. But of course, we are splitting the static of particles into two-dimensional and the three-dimensional problems. No matter what, for two-dimensional problems, we need to know how to decompose any force into x and y components. Okay? Especially when you have multiple forces acting on the same point, the best way to solve the problem is to use a component method. And actually, pretty much all example I talk about, no matter which chapter, I always use the component method, if you recall what I have taught so far, right? I never use what is called the law of sine, law of cosine. I did mention briefly here at that time, law of cosine, law of sine, but actually I never use, which means you don't have to use this method to solve. But on the other hand, if you say, I'm so good on this method of, I'm so good on geometric, the trigonometry method by taking advantage of law of cosines, law of sine, there's really nothing wrong. Okay? As long as you show the detailed procedures, we will give you credit if you do correctly. Okay? I'm not forcing you to use component method, but I myself prefer to use a component method to solve any problem in this class, because I believe this method can solve really 100% problem. And it is very straightforward. Sometimes it takes a little bit more time, just probably 5 more minutes. But you can pretty much get the correct answer. Okay? So now, how to calculate the components of a given force? Obviously, the force is a vector. You just split it into two components, x and y, and you can calculate the components based on the magnitude and the angle. Talking about this one, sometimes when during the test, students may ask a question like this. Oh, you asked me to calculate the force. Do I need to give you the magnitude of the force and the direction, or I just gave you the component? Well, what do you do when you are dealing with the homework questions? If I basically ask you, calculate the force, you can give me either way. If you like to give me the magnitude and the direction, no problem. If you want to give me the two components, then no problem either. So I don't think it's a good idea you ask me such a question. Because if you ask me the question, then I even do not know how to answer. If I say, okay, calculate the magnitude, then some other students say, well, I don't want to calculate the magnitude. You did not ask me. Why do I have to? Right? So unless I ask you specifically calculate the magnitude, then of course you have to do. Otherwise you don't have to. You can calculate the magnitude and the direction, fine, or you can just give me the two components. That's perfectly correct. Okay, so it's always consistent with those homework questions. So that's why sometimes I said, do not ask me any technical questions. If the problem itself is designed wrong, then I'm responsible. Okay, so you can complain to anything, to any extent you like, if the question itself is wrong. But if the question is well designed, and for whatever reason you may be confused, you need to try your best to recall what you did for those similar questions when you were handling those homework questions. Because otherwise, it may not be fair. If I say, okay, calculate the magnitude, and then the neighbor is busy writing something, oh, then I have to calculate the magnitude, but actually it may not be required. Okay, so just look at the description more carefully. You should be able to figure out what's the question we're really asking you. Okay, again, I never ask you very strange questions. Okay, the component method is especially useful when we have multiple forces acting on the same point. But the bottom line is, once you have all the forces acting at the same point, then you need to decompose all the forces into x and y directions. You add all x component forces together equal to 0, and add all y component forces equal to 0 to solve for two unknowns. And these are the typical two equations we use for solving any two-dimensional particle equilibrium problems. Okay, and this is what we call, this is the first time we introduced the free body diagram. Okay, no matter you like it or not, this is the basis. In fact, I keep telling you, these equations are not established based on this. Okay, this is not called the free body diagram. This is called the free body diagram. Those equations are established based on the free body diagram. Okay, so that's why I believe it's very important you need to know how to plot the free body diagram. Once you plot the free body diagram, then we know you're basically dealing with 3 forces or 4 forces or whatever, and then we check your equations to make sure those equations are correct. Even though your final answer may be wrong, that's just because of numerical mistake. If that's the case, you just get very less penalty. But if you do not draw this one, and then you did not write those correctly, then you get a lot of penalty because we even don't know whether you can draw this free body diagram correctly, because we cannot make any assumptions if you do not say anything. Okay? So that is the first part in chapter 2. And then the second part in chapter 2 is to talk about three-dimensional cases. So this part is important because the previous part in chapter 2 are really simple. It's kind of part of the special cases of college physics when we talk about mechanics problem. But for three-dimensional force vector, how are we going to calculate the 3 components? I believe that's very important, especially this is the equation we have to use frequently in chapter 3, chapter 4 later, right? And that's the equation to describe a force vector in 3-dimensional setting. It's always equal to the magnitude of the force multiplied with the unit vector. Okay? So the left-hand side of the equation is 100% physical concept, but now you are splitting a completely physical concept into physics and the mathematics, because the magnitude is physics, but lambda is in fact a mathematics, because that's called the unit vector. It has nothing to do with the force. It just basically calculated, evaluated based on the 2 points you can find, and then you can calculate lambda. So now the question, how are we going to calculate lambda? The lambda calculation is to follow this procedure, right? So basically, you just randomly pick 2 points, but you do need to know the force direction, by the way. Okay? So by now, I don't think you have any problem to indicate the direction of the force. Once you know the force is directed through this way, typically, you need to find 2 points, use end points, subtract the start point. Okay? So that means n subtract m. You have 3 components m, you have 3 components of n, you use n subtract m, and don't forget to divide it by the distance between m and n so that you can finally get this lambda. And that is what we call the unit vector. Once we get a unit vector, then we can describe a 3-dimensional force vector in terms of this equation. Sometimes, occasionally, we are asking you to calculate the direction cosines of this 3-dimensional force vector, which means you do need to calculate these 3 angles, theta x, theta y, theta z. And these are the direction cosines. In other words, they are determining the direction of the force. So again, if we ask you to calculate a 3-dimensional force vector, do you need to calculate the magnitude and direction or not? If we do not ask you, you don't have to. Okay? If I ask you calculate the magnitude and the direction of the 3-dimensional force, then obviously you do need to calculate those 3 angles. And that's the only way to describe the 3-dimensional force direction. Okay? But many times we do not ask you. If we do not ask you, typically you just calculate those 3 components. This is called fx, this is called fy, and this is called fc. So you just write that 3-dimensional force in terms of I something times I plus something times j plus something times k. That's it. Okay? Any questions? Okay. The reason I'm saying this for 3-dimensional force vector, that's equation, let me give you back again, this one, because this equation is not only used in this chapter, it will be continued use in chapter 3 and chapter 4, right? So that's why every time we have to deal with this 3-dimensional force vector. Any questions? Okay, now we are moving to the next chapter, chapter 3. Chapter 3 talk about two things. Number one, we call the moment concept, which is kind of part of the generalized force, but we just gave a name called the moment. And sometimes you want to call it torque, there's no problem. But typically we call it moment in this book. And the second part is what we call the equilibrium system of forces, or in other words, we call the equilibrium force coupled systems. Okay, so we're going to go over both of them. So the first part, we talk about moments. There are three kinds of moments. The first kind of moment is called the moment of a force about the given point. And so we end up with a moment vector. And this concept has been used until chapter 7. You know, in chapter 7, we also talk about this, right? So what is a moment of a force about a given point? So we keep using that. The second part, the second kind of moment is called a moment of a force about a given axis. This is not widely used, in fact, right? But somehow you do need to know, because this is a projection of the first type of moment. Okay? It's a projection. If it's a projection, that means it's just a scalar. It's no longer a vector. But the first type of moment, a moment of force about a point, is called a vector. In other words, for three-dimensional problem, you really have to use ijk to represent. For two-dimensional problem, you can either use I and j, or you use a clockwise, counterclockwise to represent. The third kind of moment is called a moment due to a couple. This is not the real kind of physically existing moment. It is a virtual thing, but helping us to move forces from one point to another point. And that's why we're also talking about the third type of moment called a moment due to a couple. So let's quickly go through these three kind of moments. The first one is a moment of a force about a given point. So for any three-dimensional problem, when you have a force acting on anywhere inside on the surface of a rigid body, once we know this force, if we want to if we were asked to calculate the moment of this force about any other point, point O, for example, so then this is what we call the moment of force about a point. So typically, by definition, is R cross F. And that's a very important equation, because for any three-dimensional problem, where's that equation? This one, right? So for any three-dimensional problem, typically this is the only equation you have to use to calculate the moment of a force about a given point. That's probably the only equation, because I don't think I talk about any other equation to calculate a three-dimensional case moment, right? So that's the only equation. So that's why you just have to start from this equation. And then you're going to think about how I'm going to evaluate this R and how I'm going to evaluate this force. So if we give you a simple problem, calculating a moment of a force vector about a point, just in case you have nothing you can do, if you write this equation, then at least we say, well, you know at least 10 or 20% of the question, right? If you only have 1 minute, for example, to submit your work, you can write this equation. I don't think you get 0 point. You get some points. Of course, next one, when you have more time, you can evaluate how to get R and how to get F, and then you use the cross product. And that's what I call procedures. So if I have no idea how to calculate this one, that means you don't know how to write the final answer. But if you can start from here, then at least we know you know something. Okay, so write more, make more sense, in fact. Okay, so this is the first kind of moment to calculate three-dimensional force at a certain point. And then what is R? R is the distance vector. This is a vector, right? Distance vector from the point you want to calculate the moment on to the point the force applied. So that's it for this one. This R is from O to A. If from O to A, then you're going to use A subtract O. Okay, so each person can have a different way to evaluate. The bottom line is this R is the vector using three components. A subtracts three components of O. I'm not forcing you. You have to follow exactly what I keep saying. You need to find your own way. But if your way is not correct, then of course you cannot get a correct answer. Especially if you evaluate this R in the wrong way, I assume you don't know the physics. So don't complain by that time, say, oh, that's the numerical mistake. There's not a numerical mistake if you cannot calculate this R correctly. Because I keep saying from O to A. That means use A subtract O. And that's called the distance vector. And then the force vector is to use the concept we just talked about in chapter 2, right? So basically this force equal to magnitude of the force multiplied with the lambda. I probably have somewhere. Okay, anyway, so if we go back to look at chapter 2, right? Okay, so again, this is the only equation to calculate three-dimensional cases. However, if we go down to two-dimensional cases, there's many ways. Okay, so that's why I try to let you understand for three-dimensional moment calculation, this is the only equation. Where is it? Here. But for two-dimensional problem, there's many ways. And they're really up to you. Okay, so if you believe for two-dimensional problems to calculate the moment of this force about a certain point, if you believe you are pretty good to catch what we call the short distance, d, then I would suggest you to use this way, because this is very fast. The only thing is you need to make sure you need to calculate the short distance d correctly. Because once you know how to calculate the short distance d, then you just go ahead to use the magnitude of the force, multiply the short distance d. And then you multiply these two parameters together. And then you're going to decide whether you want to write the positive sign in front or you want to write the negative sign in the front. Positive sign means if you can identify it is a counterclockwise case, or negative sign indicating it is going to be the clockwise case. Okay? So that is pretty much the easy way to figure out two-dimensional moment calculation. But sometimes you do have a challenge to calculate the short distance, including myself. Sometimes it may not be easy for me to figure out the short distance. Then no problem either. If that's the case, I would like to suggest you to go back to use this equation. Okay? To go use this equation, because two-dimensional case is the special case of three-dimensional cases, right? In other words, the coefficient in front of k is equal to 0. That's simple, in fact, right? And then the coefficient in z direction of the force equals 0. And you still use the traditional r cross f to solve the problem. If you use this one, then you can ignore how you are going to calculate d, in fact. It's very simple, but it probably takes a longer time, right? So that's why for two-dimensional problem, you need to first ask yourself, is it straightforward for me to calculate, to evaluate the short distance d? And if the answer is yes, go ahead and use this one. If the answer is no, which is normal, okay? So then you go back to use the traditional equation, okay? So going back to talk about three-dimensional cases, how are we going to do the calculation using the cross product between r vector and the force vector? There's many ways. Either you can use this one. The first row is always ijk, fixed. The second row, three components, are the, this is not typical x, y, z, by the way, right? These are the three coefficients from r vector, okay? Because we assume r vector having these three coefficients, right? So we put it here. And the third row are the three components from the force vector. But then you need to know how to calculate the determinant of this 3 by 3 matrix. Okay? So don't just leave here. But leave here is better than writing nothing. Because if you write this one, and if you do not know how to write the details, at least you get some partial credit, right? If you do not write anything, this one, we have to assume you even do not know how to, in principle, how to calculate the moment in three-dimensional setting. So back to the two-dimensional, this one should be 0, this one should be 0. Okay. There's even more general case. Instead of calculating the moment of a force about the original point, you can calculate the moment of this force about another point, B. Okay, so that is the first type of moment. We call the moment of a force about a given point. The second type of moment is called the moment of force about a given axis. In order to calculate the moment of an arbitrary force vector about another arbitrary given axis, what you need to do is to follow this equation. Let me show you that equation. This one. So this is a moment of a force F about a given axis with a unit vector called lambda. So basically, you need to first, let me give a more general one. This is the more general one, right? So this is the equation for us to calculate the moment of a force about a given axis. So what you need to do is to randomly pick a point in this given axis. Any point you like. You want to pick point C, no problem. You want to pick point B, it's not a problem either. So then, once you pick point B, then you can evaluate this R, which is the distance vector from the point you just picked to the point the force is applied on. So this R, distance vector, is from B to A. is from B to A, you're going to use A subtract B. Okay, so don't forget, use A subtract B. So this is called R, and then cross product with this force vector. Again, how to calculate the force vector? That's from chapter 2, which is the magnitude of the force multiplied with another lambda, which is the unit vector in the force direction. So after you do the cross product between these two vectors, and don't forget to have another dot product with this lambda. This lambda is the unit vector in this given axis. So this lambda calculation procedure is to randomly pick 2 points, and you can use the C subtract B or B subtract C, doesn't matter, because this given axis doesn't have a preferred direction. And that's the only exception, right? So typically when we talk about force, we definitely give you a preferred direction. So in other words, you have to calculate the lambda with the force direction correctly. But the only exception for this so-called given axis, you can use a B subtract C or use C subtract B, doesn't matter. Your final answer either positive or negative, that's okay. Okay, if you go back to recall the first midterm we had, right? Okay, that's the second kind of moment. The third type of moment is called a moment due to a couple or moment of a couple. And this is a very important concept because we frequently use this. You may not have the real situation like this, but this is the concept we frequently use in order to move one force to another one. And this is also the basis for us to calculate what we call the single force system in 2-dimensional or 3-dimensional problem. So by definition, the couple is to have 2 forces vectors which are parallel but in opposite direction, and they should have the same magnitude. So once you have this kind of special arrangement forming a couple, then you can calculate the moment due to these two special forces by picking any point you like, because the final result will be independent from the point you chose. For example, finally you get the moment due to this couple or due to these 2 forces, you finally end up with this equation. And this is in fact the universal equation to calculate 3-dimensional moment due to a couple. In other words, you need to identify R, you need to identify F. So let's say if you identify F like this, you randomly pick any one of this as F. If you pick this F, then R is from any point, another force line, to any point on this force line. So that's why you call this R from B to A. From B to A, that means A subtract B, and then cross with this force vector. Okay? For 2-dimensional problems, you can again use this one if you have a hard time to identify the short distance. If you can easily find out the short distance, then you can go ahead to use F times D. That's another simple way to evaluate the 2-dimensional moment due to a couple. And then, of course, this is not enough. You need to also indicate the direction, whether it's clockwise or counterclockwise. That's the third kind of moment. The reason we keep talking about the moment due to a couple is because once we have such concept, we can move a force from one point to another one. And this is always the illustration I would like to use. For example, if you have a force acting on point A, for whatever reason you want to move this force at point A to point O, what you're going to do is you virtually add 2 forces in this direction. The reason I'm saying virtually adding these 2 because these 2 are canceling each other no matter what. Then from this negative F and this F, you can see these 2 special forces satisfy all the requirement with the definition of a couple. Then you are erasing these 2 forces, this force, not this force, and this one. Once you erase, then immediately you're going to add a moment. That's called equivalence, right? So when you erase something, you need to give equivalence. So then finally you end up with this force left here, but you have another moment. But the bottom line is from this finally to here, you'll find out we finish the requirement by moving a force from point A to finally point O. The reason I'm saying moving a force because you see the final force, this one, is identical with this, just at different locations. But you have to compensate the process by adding this moment. And how to calculate this moment? This is the moment due to a couple of these 2. So basically it's R cross F. So that means that's the the point you want to move the force to the point the original force applied, that's called the r vector, and then cross F vector. For two-dimensional problems, you just need to find the shorter distance. If you cannot, you can still use r cross F in three-dimensional setting as well. Okay? So once we understand such concept, which is called the moment due to a couple, then actually we can move a lot of forces into a certain location. And that is finally end up with the resultant force and the resultant moment. So the resultant force is simply adding all forces in different locations together to get the resultant force. And then the resultant moment is simply the summation of each r cross each f and add them together. And that's called the resultant moment. So no matter how complicated the rigid body with multiple forces is, you finally end up with one resultant force and one resultant moment. You may say, well, that's not a big deal. For this case, originally you have three forces. You finally end up with the two vectors. This maybe have the same kind of difficulty like this. I agree. But how about if you have a lot of forces, like 100 forces, for example, you still finally end up with two vectors. That's a much more simplified scenario. So that's why this is what we call force couple system. So if you gave multiple forces, multiple moments together, you just need to calculate resultant force, resultant moment, and then you say this is the equivalent force couple system. Force couple system. As a special case, if we talk about two-dimensional force couple system, we have another concept which is called a single force system. So typically we call the certain system force couple system or force moment system. That means you have one force and have one moment in the system. But for two-dimensional problem, you can always find some point so that you can move all the forces to that point, and then the resultant moment happen to be zero. Using that concept, you can find out that location. Okay? For example, there is a rigid body like this. You have four forces acting on different locations, right? So then they may ask you to find out a single force system. The location at where, when you move all the forces to that point, and then the resultant moment happen to be zero. So how to solve such problem? So typically, you just need to randomly pick a point. Okay, you randomly pick a point. For example, you pick point A, or you pick point B, or you can pick this point, or you pick this point. No matter what, you move all the forces to that point, and then you finally end up with one force and one moment. And that force is called the resultant force, and that moment is called the resultant moment. So you simplify the original scenario with multiple forces into a single force and a single moment. And then you are going to assume at a certain point, like this point, and then you identify, where's my, well, I did not plot, right? Yeah, I think at that time I was use the projection to solve part C. This one. You first randomly pick a point. For example, pick point A or pick point B, any point you like, and then you can add all forces together. You get a single force, and you can calculate the resultant moment due to these forces, and this is equivalent to this. So then, the next step, you want to assume a point like this point. You don't know, then you can say from this point A to here, it's called X. That's a location to be determined, and then you move this one again to this point, and then you force the total moment equals zero to calculate X. And if you can find the X, which is the solution based on this requirement, then you can conclude by saying if you move all the forces to this point, and then the resultant moment equals zero. And that's called a single force system. Okay? So that is chapter 3. Any questions? But such single force system typically occurs for two-dimensional problem only. There's not easy to find a certain location for three-dimensional problem. So that's why I never talk about three-dimensional problem for the single force system. For example, like this question, right? That's the single force system, but at that time, there's only the two-dimensional problem. Any questions? Okay, so now we move to the key part, which is chapter 4. Chapter 4 is the key for this class, but actually it's very straightforward because basically we talk about two cases, right? One is a two-dimensional case, one is a three-dimensional case. For two-dimensional case, for three-dimensional case, we'll talk about this first, okay? For three-dimensional case, you finally end up with the 6 equations. But I don't want you to just simply write those 6 equations. Instead, I would like you to follow these 2 equations. These are 2 vector equations, but they are together equivalent to this 6 equation. Because this is a vector equation, you finally end up with 3 equations. And this vector moment equation, you finally end up with another 3 equations, okay? For two-dimensional problems, we finally end up with 3 equations because among these, this and this are independent. This is the trivial equation, and then you basically collect the equation in terms of z-axis by picking any point you like. So these 3 equations are the independent equations. All the other 3 are dependent or trivial equations. Okay? You need to know the typical supports for two-dimensional problems, and the most typically used support we have is called a pin. Where's the pin? S1. This pin, right? This is the original way to plot a pin very carefully, but typically if you look at those examples, we plot a simple way as a pin, as you can see later on. Sometimes we deal with a fixed support. Okay, we deal with a fixed support. With a fixed support, you basically have 3 unknowns: the resistance in x direction, resistance y direction, and then the moment resistance. For the pin, you basically have these 2. And as another special case, if we talk about rocker and rollers, we basically have only 1 reactions. There's many cases we talk about short cable or short links. Basically, the force when you cut, that should follow that direction. Okay? So this is the example I talk about in terms of cables. There's multiple ways you can cut, but no matter what, after you cut, you need to plot those forces correctly. I'm not saying you cannot cut here. You can cut here, it's not a problem, but you need to give forces appropriately. So that's why this is correct. Just in case you want to cut here, no problem. The reason I'm saying that, if you go back to look at your second midterm, right? There's one question, something related with this. Okay? So if you want to cut here, you need to give 2 forces. The reason you give 2 forces is because both point B and point D are part of the rigid body. And if that's the case, you really do not need to cut. But if you really want to cut, then no problem. You gave the forces correctly. But the reason this one, you cut this cable, you only gave 1 force, is because the other side is connected with the foundation. And you are not putting the foundation as part of rigid body. And that's the concept you have to understand in order to cut the cable. Okay, so for those of you who have questions, I would suggest you to look at the details about this example. So again, this is a typical 3 individual equations. We have the summation of all forces in x direction, y direction, and then you pick a point and to collect the moment. So these are the typical 3 equations. And for many problems, in fact almost all problems, I really do not want you to do a fancy way to solve the problem. There's no competition between one student solving the problem in 10 minutes with another student solving the problem in 15 minutes. That's not the issue. The issue is you need to solve it correctly. I really do not care you submit your papers just in 10 minutes or half of the time. Of course, if you submit, no problem. But more important, I want to make sure you solve those problems correctly. And many times, for those students who submit their papers early, it doesn't mean they get a higher score than you. So you need to make sure you check all the steps and to get those answers correctly. And then once you're confident, you can submit. Okay, we gave you enough time. That means you want to take advantage of those time. You really do not have to rush. There's really no rush. For the, if you are the first student turn your paper, it doesn't mean I give you extra credit. Right? So that's really no need. Okay, so that's just chapter 4. We also have a 2 force body and 3 force body problem. That's really up to you whether you want to understand it or not, because if you want to use component method, you can solve such problem very easily instead of knowing such concept. And of course, we finally have the 3-dimensional cases. For 3-dimensional cases, typically you just need to know you have a 6 equations. But I'm not going really asking you to write down those 6 equations, because if I really gave you a 3-dimensional static problem from chapter 4, it's going to take an hour to solve. So I don't want you to spend an hour to solve one problem. Okay, so that's why I'm not going to ask you any 3-dimensional statics problem from chapter 4. I just want you to know, typically for three-dimensional problem, you should be able to have 6 equations, but I'm not going to ask you to solve any specific questions in the final test. Okay, so then next one is chapter 5. Here, right? So chapter 5 talk about basically 2 concepts, but you can combine those 2 together because the centroid of an area is always equivalent to the center of gravity. Our goal in this chapter is to calculate the center of gravity, but we just need to identify the centroid of that area because that's the same point with the center of gravity. And the centroid calculation is what we call x bar, y bar. Okay, following the final equation having x bar equal to this one divided by a, y bar equal to this one divided by a. But in general, we're not going to ask you to do integration by yourself. So what we're asking you is basically using the composite rule where's composite rule? To calculate the centroid x bar, y bar in capital by splitting a little bit more complex area into a few simple areas. And that procedure is called superposition. So that's why whenever we ask you such question, I really suggest you to split this a little bit more complex area into a few by plotting like this way. And also you need to make sure every part should follow the same coordinate system. That's what I call the common language, so that each case can talk to each other. Okay? Now, another thing I want to point out, this one. You need to memorize those 3 cases. As I told you before, I just want to reiterate. These 3 cases may be used to calculate the centroid. So that's why you do need to memorize those 3. For others, you don't have to. Just in case I gave you, I will tell you those results. Okay? But I really want you to memorize those 3 cases. Triangular, a quarter circle, and a semicircle case. Okay, so these are the 3 cases I want you to memorize. Okay? And that is the first part, chapter 5. But there's another part, second part, chapter 5, which is to apply such centroid concept to solve some beam problems. So if we have a distributed load like this, then if I'm asking you to calculate reactions, of course, the first step, you need to plot the free body diagram. But then you still need to make the equivalence from a distributed load to a concentrated load. And that is basically finally to have this distributed load equivalent to a concentrated load and somewhere. The magnitude of the concentrated load is the area of this one, and the location, x bar, is the centroid. So that's why I call the application of centroid concept for solving beam problem in terms of reactions. So this is chapter 5. Now we are moving to chapter 6. Chapter 6 talk about applications, right? From chapter 4, basically we talk about a specific special structure that's called truss. In order to solve internal forces with a given truss, you have 2 methods. One is called the method of joints, allowing us to calculate all the internal forces. If you were given a problem asking you to calculate all the internal forces, you have no options. You just have to use the method of joints to calculate all member forces. You don't need to think about it. As long as you identify this is the truss structure, then you just use the method of joint. But many times we may say, okay, you only need to calculate a few member forces. A few means 1, 2, 3, most likely, right? If that's the case, you need to think about the second method first, which is called the method of sections. The method of sections is to make a simple cut, going through those internal the members. You want to calculate the internal forces. For example, if we are asking you to calculate the internal forces for members FH, GH, and GI, So then you need to make a cut. But before you make the cut, you are supposed to calculate those reactions. That's always the first step. So then you make the complete cut. Okay, complete cut means you need to split the structure into two parts. And then you just use the equilibrium concept to see whether you have 3 unknowns and you have 3 equations or not, right? So this is the typical way you can solve the problem using method of joins. Of course, I talk about some rare cases like this, but I'm not going to let you cut something like this because even myself may have a hard time to figure out how to make this very smart cut. I even do not know. But just in case, if I do give you this case, I'm going to tell you how to cut. But typically, I'm not asking you to solve this kind of problem. You need to have some kind of simple cut in order to solve a few internal forces. Okay, so that's called the method of sections. So now I'm coming back to talk about the first method. Part of the first method is to identify the zero forces. So that's the one I'm going to emphasize again. So basically, we're talking about 2 cases. Either when you have a joint with only 2 members involved, and there's no forces acting on this joint either, right? So you don't have 2 forces. You don't have two members. And this angle can be anything except 180 degrees, which means it can be anything except this case. So this is not this case. If this is the case, then immediately you can say the internal force of AD and internal force of AB are both 0. That's called the zero force members, okay, if you encounter this case. The other case, which I want you to understand, is having 3 members connected with the joint, and there's no forces. And among these 3 members, 2 of them are in one direction, in 180 degrees. Then the third member should have 0 force. So that means you don't have to cut. You can conclude the internal force of AC is equal to 0. And that's why I gave you quite a few questions, right? So most likely in the final test, the first kind of question, I'm going to just give you some kind of a truss structure and let you identify what we call the 0 force members. So if that's the case, again, you really do not need to do that calculation. You're supposed to find those 0 member forces in just a few minutes. So those are the questions I don't count typically as one of the major questions, because I really want you to get it down just in a few minutes. Okay? So that's what I call the 0 force members, and these are the 2 cases you really have to understand. Yes?
So just want to make sure, in the final test we have a 0 force member question, we just need to write down all the 0 force members.
Right.
That's right.
So for example, if I gave a certain structure like this, for example, right? I already talked about this. Suppose you have 3 0 force member, right? If you write 2, if you only identify 2, you won't get a full credit. Most likely get 2/3, right? And if you get only 1, then of course you're going to get half credit at least. At most, okay? But on the other hand, you say, okay, I'm going to write this. In addition, I'm going to write something else. Then it's not correct either, okay? So the correct answer is 3 members. But if you identify 6 or 4 or 5, we have to decide what kind of accuracy you can get. But most likely, you won't get full credit if you write more members. Okay? Any other questions? And this is important, right? So again, I really want you to understand those 2, okay, without using calculations. Of course, use calculation, you finally get it, but it takes an hour. So that's why I want you to spend just a few minutes to identify certain 0 force members. And you really need to go back to look at those kind of homework questions I gave you, right? Just in case you, for whatever reason, you cannot remember now. So these are the principles you really have to know. Okay, so this is chapter 6, and then we have chapter 7. That's, I believe, the most important part is to plot the shear and the moment diagram. So I guarantee you're going to have one complete question asking you to plot shear and the moment diagram in the final exam. It's going to be a complete question. Okay, I give you 2 pages basically, right? Okay, to solve such problem. So that's why you should not only plot. You should give me the procedures. Okay, step 1, to calculate the reactions most likely, right? And then you're going to decide how many segments you need to cut. Okay, each segment, write down those equations. Okay, if you do not write those equations, for whatever reason, you just plot directly, and many times those are not straightforward. How I'm going to assume you know how this you calculate it, right? So that's why you may lose a lot of credit. So that's why you do need to write it down very specifically to say in this part what kind of equation for the moment, what kind of equation for the shear force, and then the last step is for you to plot the shear and the moment diagrams. So let me tell you, for example, if you do every step correctly, but the last step, for whatever reason, you didn't plot correctly, I think you'll probably get at least 80% credit. But for example, if another student just plot directly without giving me the details, even though you get all correct, I may not give you 50% credit, let me tell you. Because I have the right to give you any credit I like because you didn't show the work. How can I know the procedures for you to solve the problem? So that's why I would like you to emphasize again, you need to show the procedures in this chapter. So shear and the moment diagram. So basically, let me just use one example. This one, for example, right? So in order to solve such problem, finally plotting shear and the moment diagrams, you basically need to start from the free body diagram for the entire beam, the entire structure, in order to calculate those reactions first. That's typically always the first step. So after you're done with the first step, then you need to estimate how many cuts you need to do. For example, you have 3 cuts, then you need to add 3 steps, right? The first step is always the free body diagram for the entire structure, reserve. And then if you have a 4 cuts, then you need to step 2, step 3, step 4, step 5. Okay, each step to solve the shear and moment function in terms of the location. And then you still need to add the last step, which is to plot the shear and moment diagrams. Okay, so you may say, wow, if that's the case, I may take more time. But sometimes, if I have a little bit more complex problem, you just have to do. That's why typically I give you 2 pages in order to solve such chapter 7 questions. Okay, one thing I can remind you, I would like to remind you, but it's really up to you, is to, if you keep cutting and then at the very end, for example, like this one, cutting here, you don't have to look at always the left side. You can look at right side. But if you go back to look at left side, there's nothing wrong either. It just takes a little bit more time. But in case you want to look at the right side, the location from the right to this cutting point is no longer x. It's the total span minus x. And I think I showed you at that time, right? So make sure you give x located correctly. And that's a chapter 7, I believe. And I guarantee you have a question for this chapter. So last part is chapter 9. Which is to calculate the moment of inertia. That's also important, okay? Because number 1, this is the after second midterm, and number 2, we talk about this in using probably more than 2 lectures, and I gave you homework questions. But the requirement is not that comprehensive. In other words, the only thing I want you to memorize is this. So you don't need to memorize those, okay? So in case I give you these kind of things, I'm going to tell you. So these are the only 2 equations you need to memorize. In other words, if you are given with a rectangular area, you need to know how to calculate the moment of inertia with this x prime. And you need to know how to calculate the moment of inertia with this y prime. Basically, they are 1 over 12 bh cubed, 1 over 12 b cubed h. So these are the 2 equations you need to memorize, because I'm not going to tell you. But then the question is, do you need to memorize others? If you want to memorize, nothing wrong, but you're not required because you have this important theorem. It's called the parallel axis theorem, allowing to calculate later on with a given structure at another given axis. So that's why I'm not suggesting you to memorize others. But these first 2 equations are something you need to memorize. If you do not know how to write down those 2 equations, then you have to do integration by yourself, which basically I showed some time ago for this, right? Okay, so the other thing is, if I'm giving you something like a W14 by 38 or something, if that's the case, of course, I'm going to give you those numbers. Okay, so you don't need to memorize anything from this slide. Okay, but I may test you by giving you W or 10, S10 by 25.4. What is the moment of inertia given with x prime? What's the moment of inertia with y prime? And then you still need to use a composite rule, or it's called a superposition, to calculate the overall moment of inertia. For example, if you go back to look at this, this example I talked about, right? So this can be split into 2 parts, and then you need to add them together by using the superposition method. Any questions? Yes?